Huh?
No need, no need, no need. You can be in your face. It's okay, fine.
Okay, fine.
Good morning, the viewers. So this is the third day of webinar lecture series, Advanced Water and Wastewater Treatment. So today we have a eminent person who implemented his technology in the field, that is also in our country, Dr. Professor Ashok Gadgil with us. Of course, good evening, Ashok Gadgil.
Pleased to meet you. Thank you.
Thank you.
My pleasure to be here. Yeah.
Of course, Ashok Gadgil, of course, we had a talk last week also. The person, he will bombard with a lot of positive energy to all. Is a very good person. So even you people can also meet later. Then apart from that, it's a good day because my PhD supervisor is also with us, Dr. R. Kandamadi from NIT Trichy. Then apart from Dr. Bijesh Misra from IIT ISM Dhanbad, Dr. Prasid Mondal from IIT Roorkee, and Dr. Manzoor Ahmad from SVNIT Surat. So last 2 days we talked about, we heard about lectures on catalytic ozonation, followed by some points of sensors and its applications for detecting bacteria and nanocomposite sensors for even for aerosol pH monitoring. So today's lecture will be slightly different. It is from 1 decade or more than 13 years of research and its outcome. So start on 2006 and it's implemented in 2016. So 10 years of experimental research and its implementation in West Bengal. So Professor Ashok Gadgil, I will slightly go read his biodata. Of course, he is talking on June 30, 2020, 10 p.m. We are hearing in July 1, 10:30 a.m. So that difference is amazing. So Ashok Gadgil has doctorate in physics from UC Berkeley. He is a distinguished professor of safe water and sanitation, civil and environmental engineering at UC Berkeley, and also a faculty senior scientist and co-lead for Water Initiative for Energy Technologies area of Lawrence Berkeley National Laboratory. He has several patents and inventions to his credit, among them the UV Waterworks, a technology to inexpensively disinfect drinking water in the developing countries, which served 20 million people in 5 developing countries in 2018. In recent years, his research has included ways to inexpensively remove arsenic from groundwater in India and Bangladesh, with new applications being explored for California's poor communities in Central Valley, inventions for removing excess fluoride from groundwater, removing hexavalent chromium from water, advanced method for capillary desalination, and full efficient stores for Darfur and other poor communities in developing countries. Since 2003, he is the co-editor-in-chief of the annual reviews of environment and resources. And since 2014, the founding co-editor-in-chief of the Open Access Development Engineering Journal. Dr. Gadgil has awarded several other awards and honors for his work, including Prof Fellowship in Conservation and Environment in 1991, the World Technology Award for Energy in 2002, the Tech Laureate Award in 2004, Haynes Award in 2009, European Inventor Award in 2011, Ziad Future Energy Prize, Lemson MIT Global Innovator Award, both in 2012, Prince Sultan International Prize for Water in 2013, Leo Ziad Lectureship of the APS in 2015, R&D 100 Award in 2016. Dr. Ashok Gadgil has authored and co-authored more than 135 papers in referred journals, and if you are searching his accounts in Google Scholar, we can see more than 6,000 citations, and H-index is more than 41. So, Gadgil, please.
Thank you so much. It's my great pleasure to be here, and thank you for inviting me to speak in your webinar series. I will start by sharing my screen. And I don't know, can you see everything okay already or not? Maybe not. I need to go and do the screen share again. Give me a second. Share. Now, can you see my screen?
Yeah, it is visible.
Okay, terrific. So I will basically just go through the slides because that way you get a visual idea of what I'm talking about, what kind of people whom we try to hope to help. They are ultimately the clients where we have to figure out how to avoid poisoning. Currently, they're getting poisoned with arsenic and how to fix the problem. So I want to thank all the funding agencies that ever funded me because this is important. And at the bottom, you will notice more than 100 individual contributors to the success of what we have done. So when I simply present this work, it is not my personal solo achievement at all. Okay, so that please take that into account. I want to start by pointing out that the World Bank decides or defines absolute miserable, near destitute poverty as the bottom about 750 million people on the planet. By bottom, I mean economic bottom, that earn less than about $2 a day in purchasing power parity, PPP, in 2015, and is corrected for inflation. Purchasing power parity, as most of you might know, corrects the income for the local prices. For example, a haircut, the lowest price haircut I can get in Berkeley costs $15 US, but it costs a lot less when I get in Mumbai. So all of that is corrected when you do purchasing power parity, okay? And where are these people? Where do they live? There is a list of countries that the World Bank has analyzed, and you can see the web page link at the bottom. Only 5 countries account for 50% of the absolute miserably poor people. This graph shows those people. The top country in that list is India, which accounts for 24% of the poorest people on the planet, followed by Nigeria, Congo, Ethiopia, and Bangladesh. So what is the big picture takeaway when we want to invent, test, develop, and implement new technologies for these people? My complaint all along, since ever I got my PhD in physics and became an inventor and engineer, has been that most of the engineers work for the wealthiest 5% of the population. And they would rather focus on creating the next iPhone than solving the life and death problem of people who are economically less capable of buying an iPhone at all. Forget it, they don't even have anything. And I'm not talking about technologies in this case, like the solar photovoltaic panel, cell phones, and iris biometrics. I'm talking about technologies that are developed specifically to address problems of these people. So it's very difficult to point to those technologies. It's very difficult to find specifically new technology inventions that take root for solving the problems of these poor people. They are left to catch things when they fall on them from the top, like a flip phone or a non-smartphone. So I want to show you an example of the arsenic work we did, aiming at people who are probably in those 50% that we talked about. The history, of course, is well known. There was a massive shift and a successful one, to drinking water from hand pumps in rural Bangladesh and India in the 1980s. And arsenicosis with all its effects emerged in the population from the early 1990s. And the photographs show people showing the palms of their hands because the arsenicosis shows up as hyperkeratosis, which opens up into ulcers, making it hard for them to work. The persons on the left side of the diagram, the two people at top and bottom left, they have lost part of their right hand, and the person on the bottom, in fact, left, eventually lost his whole arm and then eventually lost his life because of cancer that spread in his body. Now, the access to safe drinking water is a basic human right, is a fundamental human right, recognized by the UN back in 2010. It's also a prominent SDG, Sustainable Development Goal number 6. And yet tens of millions of poor rural people don't enjoy this fundamental right. They're forced to drink, the water they have to drink is contaminated with toxic levels of arsenic. About 200 million people like that must drink water that is toxically contaminated with arsenic. And a good fraction of them live in India. We don't even know what that fraction is because our surveys are incomplete. Arsenic is widely distributed in Earth's crust, but the most serious problem is in Bangladesh and nearby parts of India, and also parts of Chile, parts of US, Mexico, and so on. And as you saw in the pictures, it leads to gangrenes and amputations. What you don't see in the pictures is neuropathy, constant pain. Skin lesions you saw, ulcers, and what is worse is internal cancers and death. And also worse is the low IQ in children that are exposed to arsenic above its maximum contaminant level. In 2002, WHO called this the largest mass poisoning in the recorded history. And that remains the largest mass poisoning, the number of 200 million people with such severe exposure to arsenic and its consequences. So how bad is arsenic? Let's look at only internal cancers because that is where we have high quality data and very good predictive models. And let's ask the question, how many internal cancers can be expected in 100,000 people, 1 lakh people, drinking carcinogen bearing water for their whole lifetime, but the concentration of the toxic material is at the allowed maximum concentration. There are some carcinogens which are not allowed in the water at all, no detect, okay? Things like dioxin. But there are many other carcinogens which are allowed at a certain level that is considered safe. So the next graph, this page, shows you, as the title shows, the lifetime cancer risk of internal cancer. This is the excess cancer risk of drinking carcinogens at their MCL. MCL is maximum contaminant level, showing all regulated permitted carcinogens excluding arsenic. And they are rank ordered according to their toxicity. The one with the highest toxicity is ethylene dibromide. And if somebody drinks water at the MCL with ethylene dibromide for a lifetime, out of 100,000 people, about 12.5 excess internal cancers will develop. And then the numbers go downwards from there on. And this is because I excluded arsenic. The next graph, I'm going to add arsenic to it, okay? Note the vertical axis has changed. The cancer risk from arsenic at its MCL at 10 parts per billion is 0.7 per 100. So per 100,000, it becomes 700. And because of change of scale, all the other blue lines in the previous graph now become insignificantly, they're visible, some of them, to the right-hand side of the red bar, okay? This shows how bad arsenic is as just a carcinogen. It also leads to gangrene. It also leads to cardiovascular disease and neuropathy and low IQ. And this is at 10 ppb. We are talking about 200 million people who drink water above 10 ppb. And there, okay, that's allowed level. We have measured arsenic concentrations of 250, 500, and 1200 ppb in groundwaters of West Bengal and Bangladesh. Internal cancer risk rises linearly at these values. So you can see why it is the largest mass poisoning in recorded history ever. These these photographs are taken from the PhD dissertation research of now Professor Abhijit Das. He was studying at Jadavpur University the fate of arsenic removal units or ARUs placed in the Murshidabad district of West Bengal. Murshidabad district is right next to Bangladesh border. And technologies were tested in the lab. They arrived in these villages based on corporate donations. And they were usually based on sound technologies. They were shown to work in the lab. And he's a student and now a professor of economics, applied economics. And his interest was in finding out what is the fate of these installed technologies, how long they last, what is the lifetime, what is the economic benefit. He found in his survey that 95% of them had failed within 1 year of installation. And what we need is not a technology that works in the lab. That's not enough. The sustainable technology system must be financially viable, locally affordable, scalable, socially embedded. So in other words, the technologies had not failed. All of them actually removed arsenic successfully just fine in the lab. It is the technologists that had failed. Those systems they installed were unsustainable. They're financially non-viable. People didn't know how they worked. There were no social structures, invisible structures for their continued maintenance and repair. There was no knowledge transfer to the local community stakeholders of how vital they were for keeping their health in place. So what they had was essentially they were tying cattle, they were used to store hay. They were just in disrepair within 1 year. Almost all of them had failed. And now I'm going to jump to the science of electrochemical arsenic remediation, which is ECAR, a technology that we developed in our lab. And this schematic shows how it works. The idea was to develop something that will work within a sustainable and scalable technology system. I already explained sustainability in the previous slide. Sustainability must refer to the bottom paragraph on that slide about being financially viable, societally embedded correctly, having incentives for their continued maintenance and so on. And scalable refers to the fact that it is not one of a kind. You must be able to apply this everywhere you want and solve the problem. So how does it work? We have two steel plates, which are shown here in gray bars, which are immersed in the water. An external DC voltage is applied, which causes the anode to dissolve. Fe2 is released in the water. Dissolved oxygen from air oxidizes it to Fe3, which then coagulates and precipitates as hydrated ferric oxyhydroxides, or HFO for short. During that process, all of arsenic 3 is also oxidized to arsenic 5, which is a lot easier to adsorb and remove because arsenic 5 is ionic at neutral pH, arsenic 3 is not. So then on the sites on the coagulated HFO, you remove phosphates, silicates, and arsenic 5. And these coagulated particles all settle down. And what you have as a sludge, and clear water comes out as a supernatant, and the process is zero liquid discharge, hence is ZLD. It's a very one of the most desirable features for a place like India, where we are water short all over the country, or almost all over the country. ZLD is a very good way to go. There is no toxic chemical that anybody has to handle ever. There is no waste, liquid waste that has to be dumped. And we'll talk more about the waste disposal if we get time. And it's a safe way to go. We are dealing with very low voltages, about 10 to 12 volts maximum. So 2005 to 2009, we did work in the lab in Berkeley, understanding the basic fundamental science. So there's a Berkeley lab photograph, 0.2 liters in that little beaker. By 2010, we had gone to Amirabad High School in Murshidabad district on the 100 liters scaled up reactor that we first tested in Berkeley. Then we built the same reactor in India using Indian labor and so on. And there is my PhD student, and we worked it out there. By 2012, we had designed a much larger reactor, 600 liter reactor that you see on the left-hand side. Two of my students are standing in the back. The big tank in the foreground is the reactor's tank, and the tank in the background is for settling the sludge. After testing it and being happy with it, we moved it to the high school in Dabdapi. That is a 600 liter reactors. And you see, I'm explaining to other faculty at Jadavpur, who are our very close collaborators on social science side, as well as on the engineering implementation. And then from 2013, we scaled it up to 2,800 liters, two reactors of 1,400 liter each that you see on the photograph now on the right. That was also in the Dabdapi High School in a classroom that the school gave us in exchange for our promise that if the technology works, then all 2,500 students and 400 staff and teachers will get free arsenic safe water for good, so long as they let us use the room and operate the plant. And we'll pay for the electricity as well, so long as we are allowed to pay, sell the water to the community. Here by we, I don't mean Berkeley. I don't even mean Jadavpur University. I mean a private licensee that was going to take over the plant and operate it for profit, employing local people and selling the water to local people. So we pursued three tracks in parallel: technology, which is kind of science, fundamental science. Here we are showing you an electron micrograph of these coagulated particles, and then education and outreach to the teachers and the students of the Dabdapi school and to the community. So the schematic process diagram here, just very quickly, there's a groundwater pump which feeds water into the steel plates. You see the ECAR as parallel plates, from which it goes through a flocculation chamber, from which it goes through a tube settler. Very clear water, maybe NTU of about 5, emerges, then goes through a rapid sand filter, micron filters. NTU is about 1 or less. We add a UV disinfection stage just to be sure, even though we know that electrocoagulation kills bacteria and viruses already. But this is an extra safety measure. And then there is a electronic water distribution, as you will see. Here is the two reactors, 1,400 liters each. Very nicely done job. All the cables come from the top. Here is the iron plates. As you can see, they're interdigited plates. So you can see them like fingers from two hands going into each other, alternately anodes and cathodes. Here is a team. The pilot plant was designed to treat 10,000 liters per day. And the student, the girl sitting in the front, in the center, she is my PhD student. Everybody else is actually local faculty standing in the back from Jadavpur University. The lady on the right-hand side standing is the head of the West Bengal Pollution Control Board, whom we had invited to inspect what we were doing. This is what the data looks like from April 11 to January 30, where we actually flew samples all the way to Berkeley and also sent it to an NABL certified lab in India. So we double checked everything. And so initial arsenic concentration consistently was 252 plus minus 30. But you see the scale only goes up to 12 ppb. The blue line, horizontal blue line, is 10 ppb. The average is 2.9 ppb. We did not give this water to drink to any human being during the gray part of the picture, which is until about 15th of September. We were only monitoring it and throwing it away. Only after we were extremely confident that we understood everything of what was going on, and after obtaining all permissions from relevant authorities, we moved on to from 15th of September. And there you can see the water actually is less than 2.9 ppb, right? And it has been operating there routinely after we left. The electronic dispensing is by giving students cards, electronic cards, and there is an electronic monitor, and this is a photograph with the boys and girls collecting water. What is the impact? As you saw, the cancer risk is linear. So at 250 ppb, the cancer risk being linear is 18 internal cancers over a lifetime per 100 people. If arsenic was at 10 ppb, the arsenic risk is only 0.7 per 100 rather than 18 per 100. Even 0.7 per 100 is way too much, I think, but that is at 10, and we deliver water at 3 ppb. So as a result of what we are doing, if that plant was operating on, and if it was affordable and it was financially viable, which it is, we will reduce the risk from 18 per 100 to below 0.7 per 100. So it's a 60-fold reduction in risk. And that is achieved by selling the excess water at 1 cent. Actually, it is 6 rupees per 10 liters. That is the price at which it is sold to the community. So it serves about 8,000 people, of which about 4,000 are school people who get it free. So what's the big picture takeaway? The same question I started with. And why there are so few technologies, new technologies, that take root in solving problems like the one I described. We hypothesize that there are two major failures and disconnects which causes the people at the bottom of the economic pyramid to be left to simply catch the crumbs that fall from the table of the people at the top. First is that most engineers in their formal education are clueless about how the world outside their deep and narrow discipline, how the rest of the world works. And this is not just true of engineers, it's also scientists. Okay, I'm a physics guy, so I know physics is just like that. So it's good for going or being sent to the boiler room, is the basement, or the bottom of the ship. But if you want to be up there in the captain's bridge, then you need to understand a lot more. And you need to work with economists, we need to work with sociologists, and we are not even taught the vocabulary. And in the first world, I argue, this vocabulary is often not needed because the first world institutions are highly differentiated and well-funded, that there is enough expertise and enough glue for these experts to come together and work. That doesn't happen for the developing world, where everybody is trained according to the Western model, and you are only taught your discipline narrow and deep. And you would not understand what is this thing called discounting rate for future savings. You wouldn't know what is the theory of diffusion of innovations. You would not know what is called a change agent in a social network, because I wasn't taught that either. Okay, but for the first world, it doesn't matter. for the developing world, which is majority of the planet, it matters. And my own contribution, part of it, Dr. Nitish mentioned, is to start an open access journal called Development Engineering that tries to see what can be done, how to integrate these disciplines. And then second point is there is quite inadequate appreciation of what it takes to cross what we call the critical zone, to go for, as the technology goes, progresses from the lab all the way through field testing to a technology that is financially viable, that is economically viable, that somebody will invest in. Here is a picture of the critical zone effort in yellow, but I want to walk you through the purple arrows first. You go on the top in the purple arrows from idea. For some of us who use a term like technology readiness level is TRL 1 and 2, all the way it goes until scale up. On the bottom, the green bars show the expected cash flow. And I want to point out that the scale of the expected cash flow goes negative, negative, negative until you build a large prototype, and then you go from there to first commercial. But note that the scale is logarithmic. IBM, for example, expects that the large prototype will cost 10 times more than the cost of development. Okay, so there's a huge dip in the cost, and nobody funds it, except unless you have a real funder who wants to make that transition happen. So effectively what happens is people do small prototypes, publish papers, and they get frustrated. It sits on the shelf in a journal and makes no difference to the real world. So what did we do to cross this critical zone? What are our lessons learned? We designed a community scale system. We increase the economic opportunity for community members by designing something that employs local people. We bridge the knowledge divide by making proactive effort to go out to the community and holding public meetings every 4 to 6 months, outreach. And we ensured that we are respectful of all regulations, local, state, and national level in India. So don't you come in messing with it saying we know anything better. You might know better, but you have to follow the local regulations and work with the people who are responsible for enforcing it. And then the user experience, which is essentially what you see, that electronic card, students A in panel A, and in panel B, the schoolgirl is just entered her details on the card. Panel C shows the electronic dispensing unit, and a water queue in panel D. So that works well. Now we have time to see a few slides of our current technology research. So I bring you up to 2020 in my lab only, what we are doing. And I'm going to show that, given that we have a little bit of time, hoping that there is more time left over for having discussion with the panelists, with permission from the chair, Dr. Nitish. Can I show 4 or 5 more slides?
Yes, you can proceed. Please proceed.
Okay. So the next generation of e-car is something called an air diffusion cathode assisted iron electrocoagulation. If you remember, in the previous pictures that you saw, the anode was the one that was doing the dissolving, and the cathode was sitting there evolving hydrogen. Now, instead of that, we have an air diffusion cathode, which is made out of a water repellent porous material like felt, conducting felt in which we impregnated carbon to make it conducting, and it's hydrophobic. So oxygen can come and contact the water. And that is where you have the cathode operating that produces H2O2 at the cathode. So now you have dissolved Fe2 that turns into aqueous Fe3 oxides. Aqueous arsenic 3 turns into arsenic 5. And that reacts with Fe2 10,000, about 10,000 times faster than dissolved O2. So far more faster reaction kinetics makes very high flow rates possible. The Faradaic efficiency of generation of H2O2 is about 80% at high current densities, which is what we operate at. So we get lots of H2O2. There's no depletion of dissolved O2. There is some H2O used up in the reaction, but we also leave some H2O2 to go forward in the water to be used for disinfection or whatever else you want. This is ECAR, okay? I'm showing you what happens with ECAR using synthetic Bangladesh groundwater in the lab, spiked at 1500 or 1460 micrograms per liter or ppb. And we operate the ECAR in 3 different modes. To speed up the reaction, we can go to higher and higher currents or coulombs per liter per minute. And the lines are not meant for just anything to guide the eye. So you can quickly see the black spots, red spots, blue triangles. You can see how you can bring 1560 or about 1500 micrograms down to maybe 100 micrograms if you work very slowly. Okay, that is the black squares. But the moment you start jacking up the current from 3.2 coulombs per liter per minute to 63 coulombs or 120 coulombs, the arsenic removal degrades rapidly. Okay. Now I'm going to compare this, and in all cases, we are delivering 300 coulombs per liter at the end of the process. The 3 experimental cycles simply show you replicates, okay? This is what happens with Acai. Same 3 currents, okay? Same 300 coulombs, but now we are well below 10 parts per billion. So what we could not achieve over 90 minutes of ECAR, we can do in 2.5 minutes in Acai. And that is because we don't have the bottleneck of kinetics anymore. It's dramatic, it's so exciting that we can now deliver very high throughput water by very short residence time. This is the similar graphics essentially showing you the treatment duration. Now we are looking at 600 coulombs per liter. On the left-hand side is ECAR or FEEC, and we deliver 600 coulombs per liter in 3 hours and 20 minutes. On the right-hand side, Acai, we deliver 600 coulombs per liter in 30 seconds. And in both cases, the final arsenic is less than 4 micrograms per liter. That is so exciting. We got this result just last year. This year, now current work is we want to demonstrate successful remediation of real groundwater in California, rural California, poor village site, poor by American standard. Nevertheless, there are also people who are left behind. And on the left-hand side, you see that how the final arsenic has dropped all the way below 132 parts. From 132, it has dropped below 10 by the time we go to about a dose of 50 coulombs per liter. Task 2, which is ongoing, but now we are hit by this COVID epidemic, so the labs are closed for a while. But we are restarting our labs next week very, very cautiously. That's the university level decision, is to build a single box about the size of maybe 2 or 3 laptops stacked on top of each other, is what you see called 60 LPH, liters per hour, Acai system. The physical volume is just 3 laptops stacked on each other. And then we get 10 of them stacked on top of each other in a rack. And then you get 600 liters per hour water throughput. That is the goal. We are delayed a little bit. We'll get there, we think, in a few months. So I'll stop here. So we have time for panels, questions, and some discussion. So I want to thank you very much. You'll see my email address there. You'll see the lab web address. And that was my last slide. So now I will stop sharing. Am I correct?
Yes, yes.
All right. Here we are.
Yeah. Thank you, Professor Ashok Gadgil, for this wonderful talk. So now we can go for panel discussions. Professor P. Mondal, please. Please on your mic. Switch on your mic. Professor Mondal? Yeah, oh, it's fine.
Okay. Yeah. So thank you, Professor Gadgil, for nice presentation and enlightening us with the results you have obtained during last 10 or 15 years. So really it was very, very interesting to see that how you are able to produce water with minimum expenditure, a very cheaper process we can say. I have some query. I'm also aware about another development in this region where the same electrical process is used, but no sacrificial electrode is used in this case. Without with using non-sacrificial electrode, they are producing arsenic-free water. So in that case, and your case, if we compare, then in this process, in your process, one major problem comes with the sludge management. So how this will be handled?
Very good question. I was hoping somebody will ask me about sludge management.
Yeah.
I want to start by saying that 600 coulombs, even if you deliver 600 coulombs per liter in e-car, let us say, that works out to be 200 milligrams of iron delivered to the water per liter. So the amount of iron delivered in Dabdapi, where the intake of water is 250 ppb and the charge that we deliver is 450 coulombs per liter, the amount of rust that is produced is about 250 grams per person per year. So the volume of sludge produced is very small. The sludge itself passes what is called, US EPA has a rule called TCLP, Toxic Leachate, Chemical Leachate Protocol. It passes TCLP. We do not find any protocol yet announced by any government, either state or national in India, central government, for disposal of such arsenic-bearing waste. So we contacted with a chemical hazardous waste disposal company called Ramki that operates in the local area in Bengal. And Ramki is contracted to take that waste to the hazardous chemical disposal waste site at Haldia, I believe. There is one there at Haldia. When we told them how much waste there was, they basically laughed at us saying, you know what, this is so little, it's not worthwhile for us to come to pick it up. So we are going to leave it there for a whole year until it accumulates. So keep it in a cage and we'll come. And because you're doing this work for the public good, no, we'll just take it for free, which is very sweet of them. But we still insisted to find out how much will it cost. And the cost of that sludge disposal is less than 1% of the price of water. The price of water is 6 rupees per 10 liters. Out of that, 6 paise will go towards sludge disposal if we were to pay them. But all of this is happening at profit to the operator. The operator of the plant makes about 1 lakh rupees of profit per month, including the cost of electricity and paying 2 part-time operators and paying for the steel electrodes, which have to be replaced. So financially, it remains viable, very attractive, in fact. Lastly, Jadavpur University and also people in the US, but not at Berkeley, have looked at immobilizing the sludge in concrete as a way to not allowing it to spread. Even though it passes TCLP, you don't want it to fly around as arsenic-bearing sludge. And it turns out that the results from the civil engineering department in Jadavpur show that 60% of sand in a mix of concrete, 60% of sand can be replaced weight by sludge. And the strength of the concrete blocks has kept on increasing up to 60%, after which it declines. So it is possible to embed it in concrete, which is what is also the way the Chinese like to dispose of iron sludge, which is used as an adsorbent by mixing it with concrete. So there are ways to dispose of it eventually, but we currently don't have any rules. But I did not know about this new technology you mentioned called, without doing any sacrificial anodes, they use an electrical process to remove arsenic. What happens to the arsenic atoms? Where do they go? They have to go somewhere.
Yeah. Actually, the chloride is there. So chloride, some hypochloric acids and some functional changes takes place, and which oxidizes arsenic 3 to arsenic 5, and it settles. There also sludge problem is there.
Yeah, they have to have it. No, arsenic atoms, you have to get rid of them somehow.
But less, the amount will be lesser, because in that case, the sludge directly the iron which is available in water itself, that is capturing the arsenic 3, arsenic 5. But in this case, the sacrificial electrode is used and more ferrous or ferric hydroxide is produced. So the sludge will be higher in this case, but in non-sacrificial electrode, the sludge is less.
Oh, so how do they add iron? Well, look, we can talk offline.
Yeah,
I don't want to slow it down. Okay, I would like to learn what other advances are there. Okay, sure. Okay, thank you.
Thank you, Professor Gadgil.
Dr. Brijesh Mishra, please proceed.
Sir, very nice presentation, sir, and I am happy because I am also working on the same field. My intention is only saying when we are talking about ECR, so H2O2 formation is going to be there, and groundwater have an organic component, organic carbon.
Correct.
And it is going to form some byproduct, because I am treating coke on wastewater, that time byproduct formation, and here I did, my paper is published in Water Science and Technology. So byproduct, especially that is the main target, because we are able to remove arsenic, and it may possible that some other byproduct is going to form too, because whenever we are talking about electrocoagulation, ECR, whatever, when it is in the presence of electrolytes. So I am concerned about your studies that included that byproduct formation. Yes, sir.
We have always worried that increasing natural organic matter will be a quencher for the Fenton reaction also.
Yeah, yes,
because it is a sink for the oxidizer. Whether you currently without the H2O2, we use the Fenton reaction pathway to create arsenic oxidation from arsenic 3 to arsenic 5. So we always had to watch out. Earlier, we watched out in Berkeley by adding NOM artificially that you can buy off the shelf as a standardized one. And we also checked the amount of NOM in the groundwater at multiple places in Bangladesh and in West Bengal. It doesn't seem to be a problem for us at all. We are the kinetics of NOM removing the Fenton agent essentially, because arsenic, it goes up to iron 4, and then it could just quench it by absorbing the oxidation potential of iron 4 before it drops down to iron 2. I'm sorry, iron 3. That is not, the kinetics are not that fast. It appears to us from experimental work that in presence of the NOM, that the small amount that is there in the groundwater, we had no challenges in removing AS3. The data I showed you running is, we normally challenge our setup with only arsenic 3, because that is a harder one to remove always, and it requires extra step of transformation into arsenic 5 before adsorption. So all the headaches have to be overcome. Now we are sure it works fine. But in real life, in the samples that we tested, arsenic 3 and arsenic 5 appear in equal proportion. So some of the arsenic is already there as arsenic 5. That means we have less work to do. For no need to convert that 5, and only 3 we have to convert. That seems to go through just fine. But you're right. If there was in principle a huge amount of NOM in the water, we could be in trouble, right? So one of the things we have to do is test to make sure that the NOM load on the inlet water is not so high. So we must test the water every time, because every water matrix, as you well know, will vary from place to place depending on what is the upstream hydrogeology of the water source.
Because of that, my intention is, if that water have NOM, first we have to pre-treat that water to remove that NOM. Otherwise, it is going to make byproduct, and at the same time, it is going to hinder the arsenic removal. Thank you.
You're right. It could impede the arsenic removal if the NOM is very high. Fortunately, H2O2 based oxidation of NOM is not going to give us the halogen byproducts which are carcinogens. It will do something else to the organic matter. It will oxidize it, not completely oxidize it, not CO2 and H2O, but it will do something else. Maybe it will start floating as a oil with a very higher melting point.
DBCM, BDCBM.
Yeah, very valid point. We have to test the water, and if it is particularly contaminated with industrial NOM, we have to watch out.
Thank you, sir. Thank you. Thank you.
Thank you.
Ma'am, please.
Yeah. Yeah. Good morning, sir. It's a very nice presentation, especially with the application to the real field problem. I have some 3 questions. The first one is, what is the basis for selecting the iron electrode over aluminum electrode? Okay, in your studies, you have used only the iron electrode.
Correct.
Then second one is, what is the that concentration of iron in the treated water? Do you have any studies with iron concentration in the treated water?
Yeah.
Then third one is what is the lifetime of that electrode? Because your studies, you are treating with 1,200 liters per hour and then very high flow rate you have used. Then what is the lifetime?
Sure. Good questions, and all valid questions. The reason to use iron and not aluminum is that we wanted to tap into 2 features that iron has, which aluminum doesn't. Iron allows us to use Fenton chemistry so that the Fe2 with dissolved oxygen or with H2O2 will jump up into Fe4 transient state, which acts like a nice oxidant, and then it drops down to Fe3. In that dropping down, it oxidizes both arsenic 3 to arsenic 5, and it also oxidizes some more Fe2 into Fe3 also. So depending on the relative concentrations of arsenic and Fe2 production rate, the Fenton reaction when Fe4 goes to Fe3 will be split. There will be 2 competing pathways for that. Aluminum doesn't have that extra capacity for us. So if we were to use aluminum hydroxide to capture a precipitate, we will have to externally oxidize somehow AS3 to AS5.
Yes.
And AS3 is very common in groundwaters. About half of the arsenic content is AS3.
Yes.
So people have tried maybe adding chlorine to oxidize AS3 to AS5 separately, and that causes one more supply chain problem.
Okay, sir.
So we avoided all of that by just using God-given oxygen.
Yes.
That does the whole job. We don't have to do any work because nature does the work for us. Why we are lucky that way. We did not know it will work out so well when we started. So that is the purpose of preferring. Also, pound for pound, of course, iron is cheap. The steel that we use is ordinary construction steel. Ordinary construction steel used in India all over the place. We make it in vast amounts in the country.
It not costs stainless steel.
No. It is ordinary construction steel, ma'am. Very simple stuff. No, nothing expensive at all. No.
Okay, sir.
It's just ordinary low carbon steel. It costs $1 per kilogram. That's my recollection. So like you go to any construction site, they have steel sheets. You could use anything like that also. That is one. Secondly, the iron content in treated water is actually lower than the iron content in the raw water.
Oh,
By conversion to Fe3, coagulation, settling, all iron is removed.
remove.
As a side benefit, we also remove phosphate. So people who taste the water in Dabdapi say that, of course, they cannot taste the arsenic. They know that, we know that, but they say still the water tastes better now than it did before, because the slight amount of iron is now gone and the slight amount of phosphate is also gone.
Yeah, yeah.
So it is gone. So we are very, very clear on that. Lifetime of the electrode will depend on the thickness of the iron plates. We all know, we knew from the start that iron plates will eventually get passivated or they will collect more and more and more rust.
Yes.
And our argument was collection of rust on the surface as opposed to release of the Fe2 ions in the water. There is a competition between the two. If you allow the rust to accumulate, then the Fe2 cannot get released in the water. It just goes in the rust layer, which gets fatter and fatter. So part of our operating protocol for these two workers who are employed is at the end of every day, they must take one of these stiff plastic brushes that we have given. It's one of these bottle brush kind of thing. It's a rod with bristles coming out that was fabricated by a shopkeeper here in Calcutta. And they push it between the plates once down and up. So it brushes away the thin layer of rust that sticks. And that is all they have to do. If they don't do it, then of course the rust layer grows. And then you don't get any rust in the water and things really get out of control. But that is true for every technology. Even if we look at simple technologies like a kerosene lamp or a bicycle, somebody has to take care of a little bit of maintenance. Otherwise, the technology will always fail. No? So this is all we had to do to keep the iron electrodes functional is soft brushing every day, once a day. That's once a day is too much, but we said just do it every day, damn it. It's better to be safe than sorry.
Okay, sir.
Dr. Mansoor, please.
Thank you, Dr. Gadgil, for a good presentation. I have two questions. One is that is the process continuous or batch? Or second question, why don't we use reverse osmosis process for this? Because we understand in terms of technology, X-ray, it is much better. I mean, it is well proven. Why don't we use that? Is it because of the cost involved?
Okay, good question, both of them. The process for ECAR is a semi-batch process, which is why we have two reactors. When the water from the first reactor, 1400 liters, is being treated through the flocculation and tube settler, then the second reactor is already working, which is why we have two reactors. So it is pretty much like one after the other. Each reactor is processing or charging and emptying. So we can run, the output is continuous, but the reactors are two because they can be loaded up and unloaded or can be electrolyzing either of the two modes. Okay, so it's a semi-batch process so far as the reactors are concerned, because as you saw in the discussion, the iron EC is a slow process. It takes 90 minutes in Dabdapi for the water to get 450 coulombs per liter because we have 1400 coulombs. 1400 liters times 450. Okay, so by alternating the two tanks, the tube settler gets a continuous flow of water. The output is continuous, even though we actually store the water after treatment in the stainless steel or some safe tank from which it comes down by gravity to the dispensing units. When it comes to Asahi, it is strictly a continuous process. There's absolutely nothing stopping us. Water comes in from one side, goes out the other side. The size of that little Asahi reactor that you had described as it's about the 3 laptops put on top of each other. That volume is 1 liter. And the residence time in the reactor is 60 seconds. So you get 60 liters per hour through that box with a volume of 1 liter, right? So Asahi is a continuous process. ECAR is a semi-batch process. And for drinking water, it seems to be fine for ECAR. But in the future, we would like to go to a continuous process that is more compact than ECAR. But ECAR works well, at least for sure, for now. Given the risk of consequences from arsenic, I will take it over having nothing else. The reason we don't want to go in the direction of RO is because near circumneutral pH, arsenic 3, which is half of the arsenic content, is non-ionic and it goes through your RO membrane. It's only the arsenic 5 that is captured well in RO. About 20% of arsenic 3 will go through. So that is one reason. And the second one is, of course, waste. Liquid waste is not a zero liquid discharge process. So we have 2 benefits of using, not going down the path of RO. One is we not waste water. All water molecules that we start with will end up in the drinking water, clean. Only arsenic and phosphates are removed. And the iron sludge, of course, is removed. Arsenic, initial iron also goes down. But RO will not remove arsenic 3, not well enough. Not if you have 250 micrograms per liter of arsenic at 50-50 ratio. I hope I answered your question.
Yes, sir. Yes, sir.
Okay.
Okay, thank you. Thank you, Mansoor, and other experts members for joining with us. Professor Gadgil, I have a few questions. Can I?
Sure, okay. Of course.
Okay. So we are also, one of my PhD students also working on the same, just like your essay. Because see, hydrogen peroxide generation will always take place in the acidic conditions. Because 1 proton is enough required for generation of hydrogen peroxide for the 2 electron reduction of oxygen at the cathode. So how will you maintain? Because normally in groundwater pH will be around neutral conditions. So is there any mechanism, or we need to reduce the pH?
No. We don't need to reduce the pH. We operate at circumneutral pH again and again in multiple places, right, with no pH adjustment. Of course, the water is naturally buffered, so we don't have to worry about the pH swinging too much. It's not like deionized water. But we get 80% conversion efficiency, Faradaic efficiency, as I mentioned, okay, for H2O2 generation at the high current density end. At a low current density end, the conversion efficiency drops to maybe about 45 or 50%. But we get copious amount of H2O2. We don't need acidic condition there. Okay. Not externally for the bulk water. Sure, right, you're right that in the electrochemical layer, right next to the electrode, the pH has to shift. Sure, we know. Right. Yeah, but in overall, we didn't have to change the conditions at all. It works very well.
Okay. Because even we tested the same system in different pH conditions.
Yeah.
pH 3 is even low pH.
Oh my God.
pH,
okay.
And in higher pH, even in 9 pH.
Okay.
So because see, even normal, if you are using sacrificial anodes like iron, then the pH will shoot generally because of hydrogen evolution reaction at the cathode. So
the water is naturally buffered in our case.
Okay.
Because of the natural constituents,
right,
and the pH doesn't shift. It may be shifted by 0.5 at all, if at all, throughout the whole process.
Okay.
So it's all natural buffering, huh?
Okay, but in general electrocoagulation cases, it will shoot in maybe in neutral conditions. There may be a shift, maybe around 3 pH
My
from,
God, three whole
yeah.
integers, 3
Right.
points.
Right.
But with groundwater.
I didn't check with the real groundwater, but normal,
okay, yeah.
normal
Okay.
reactions because of hydrogen evolution reaction. At the
No, I
cathode.
understand. Sure, of course. Right.
So even high pH, it is working.
We had no problem at all. Yeah. In fact, your internet is frozen, it seems. Can you hear me?
Yes.
Yes, sir.
It's an.
Oh, you are here. Okay, good. Yeah, for a little while there was a glitch, but go on, please. Yeah.
Okay. So that's why there may be some buffer system should be there because of the pH shoot up. I think in groundwater, I think it will really work well. Another thing is in normal assay, what you mentioned, cathode should be a carbonaceous electrode because hydrogen peroxide generation is effective in carbonaceous material.
Correct.
At the same time, what is happening is in iron, it will produce hydroxides of ions. So that will attach in the cathode. So it will give the layer formation. That means we can call it as a passivation of cathode. How will we stop all these things?
Very good question. Very, very good. I'm glad you caught that, or your student caught it with you. Very good. So two things happen on Acai. One is that there is a deposition because of alkalinity on the cathode side. If you push the pH in the electrochemical sublayer, you will end up getting deposits of calcium and magnesium calcite, for example, on the air cathode, depending on how much calcium magnesium you add. And lots of groundwater has lots of calcium magnesium. So end up building those deposits. But in our experience, even though it makes the appearance of the air cathode look whitish because of those deposits, its performance does not decline at all. Okay, so that seems to just go through, and we are able to clean the air cathode by washing it with, say, citric acid or things like that. Just give it an acid bath or organic acid even, and calcium magnesium will dissolve out into the solution. So that is always possible. That is not a worry. Okay. The second point you made is absolutely right, that if ferric hydroxides deposit on the air cathode, they ruin the air cathode's ability to generate H2O2. So we had to develop ways to engineer the hydrodynamics of the cell so that the FeOH generation, Fe3OH generation happens downstream of our air cathode. You can do them sideways. Suppose the flow this way. You first hit the cathode, generate the H2O2. The water keeps on going up. Then you hit the dissolution of the anode, and the water keeps on going up. That's it, gone. There is no way for the flow back because of the flow itself is downstream. That is one way to do it. But there are other ways to design the reactor any which way, but I just illustrated one because time is short, but different ways to engineer the reactor so that the FeOH thrice does not, Fe3OH hydroxide, does not come near the air cathode, because if it does deposit, you can dissolve it, of course, but it will ruin the H2O2 production. Right. And then the whole reactor begins to not go so well.
Okay, thank you.
Good. We are working on the same problem. Good.
Thank you, Professor Ashok Gadgil, for this informative talk.
Sure.
Even there are a lot of issues with the electrochemical system, exclusively with the scaling of electrochemical system. There may be a lot of challenges.
I know.
Anyway,
But I took a I must say, I took a labor-intensive approach to addressing them, because we tried everything else, such as ultrasonics, this, that, and automation. And then we said, you know what? if some people get local employment at a really low labor rates, they will be invested in the success of the plant.
Okay.
And they are also seriously dependent, because the guys were originally plumbers, okay? And as plumbers, their income was sporadic, not constant. Only when there is a job, they will run around from house to house. Now they have a regular steady job. So we already have some guys, our champions, saying, you know what? I am the operator of this plant here.
Okay, okay, good. So I really thank Ashok Gadgil for this wonderful lecture, and he accepted with a single email, said that okay, I will give a lecture, and it's a wonderful lecture for us. Even from 2006 to 2016, that means from batch to the implementation stage. He focused mainly on the electrocoagulation, ECR, and its application, challenges, everything he covered, and it is a good enlightening for the initiators. And I also thanks all the panelists, Professor Mandal, Professor Mishra, Dr. R. Gandhimadi, Dr. Manzoor, for joining us and have a good discussion with us, with Professor Gadgil. Thank you, everyone. And I also thank the viewers for watching the program. And for the viewers, tomorrow our program is at 12 o'clock in the noon time. Professor Gerasimos Libertos will join with us tomorrow with wastewater treatment using microbial fuel cell technology. So till then, bye. Good night, Dr. Ashok Gadgil.
Bye-bye. My pleasure. My pleasure. Thank you very much.
To all of you.
Take care. All the very best to you. Thank you.
Yeah, thank you, Dr.